SharedNeRF, leveraging photorealistic and view-dependent rendering for real-time and remote collaboration. In collaborative tasks that involve physical artifacts, having the ability to observe the task space in high fidelity from multiple viewpoints is important for smooth collaboration. Sharing a physical object remotely presents challenges, often failing to offer the perspective needed by a remote collaborator. Point cloud rendering facilitates real-time sharing of a task space, allowing for free viewpoints in 3D space. However, it often lacks the necessary fidelity, leading to issues like noise or missing meshes. NeRF, or Gaussian splatting, on the other hand, delivers high-fidelity and view-dependent rendering of physical spaces, but is slow to update due to training times. In our work, we leverage the advantages of both rendering approaches to enhance the remote sharing of physical spaces in synchronous collaboration. To train a NeRF model, the system uses Orb Slam to track camera poses from a head-mounted camera worn by a local user. These poses and images are transmitted to the remote side and added to a dataset for training. To enhance the NeRF model over time, the system optimizes the training dataset by maximizing the diversity of camera poses. A stationary camera is used to detect dynamic movements or changes in the scene. This detection informs the system when to introduce new training data or refresh the dataset, allowing the NeRF model to adapt to the scene's current state. Using this technique, as the local user alters the scene, the system updates the NeRF representation accordingly. Any changes made by the user are reflected in the NeRF model, enabling the sharing of the scene's new state with the remote collaborator. To share dynamic elements of the task space with a remote user, overlaying point cloud rendering onto NeRF using the Z buffer can eliminate the black patches commonly seen in point clouds by replacing them with NeRF. It also visualizes moving hands as point clouds, with the hands occluded by objects rendered through NeRF. However, relying solely on the Z buffer can lead to an issue where moving an object might cause it to be duplicated in the renderings produced by both NeRF and the point clouds. To ensure that the system renders dynamic elements with point clouds and static elements with NeRF, we use color and depth data from both NeRF and point clouds to create a dynamic mask. This mask determines which pixels should be rendered through NeRF and which through the point clouds. Our shader uses a weighted average to merge the color and depth masks to enhance the quality of the blended rendering. Here is a demonstration of using SharedNeRF in flower arrangement. The remote collaborator can examine the flower design while adjusting their viewpoints for better observation. They can also view real-time hand gestures through point clouds, as well as the local user's attention through their 3D avatar. When the remote collaborator specifies a flower, the local collaborator adds it to the arrangement, allowing the remote viewer to observe the dynamic elements in real time. The collaborators can review the completed design, focusing on various elements of the flower. Here is another example of computer inspection, where the remote collaborator examines the computer's setup to identify an issue. The remote viewer can see the real-time movement as the local collaborator connects the cable to the GPU. The remote collaborator can review the new configuration, taking a close look or stepping back to have a broader perspective. In our preliminary study, participants completed a flower arrangement task under 3 conditions. The participants highlighted the benefits of having independent viewpoints over the video condition. They also appreciated the visual fidelity of SharedNeRF compared to the point cloud condition and noted that the moving hands and objects helped them understand the dynamics of the scene.